Hello everyone, this is Mr. Jackson, and today I'm going to be going through the practice dihybrid crosses activity with you. So for this, we've got a few problems where it gives us our examples, and we use our dihybrid crosses and our parent genotypes in order to not only provide ratios for potential offspring, but also answer some questions, either on numerical basis, like how many of which will be what, but also maybe percentages and ratios and the like. So let's go ahead and get started with problem A. We're going to be going through all of these in this video, and I hope that you find this helpful. Okay, so it says tall sunflowers are dominant to short. Okay, so again, doesn't really tell us what letters to use here, but since tall is dominant, I'll say tall is an uppercase T and short is a lowercase t. While yellow flowers are dominant to orange. So again, yellow, I'll use a capital Y. Orange, since it's recessive, I'll use a little letter Y. It tells me to cross a plant that is heterozygous for both traits. Okay, so for this one, I can just put each of these in the parent genotypes. If it is heterozygous for both, I know it's big T, big Y, little y. And it says cross that with a plant that is homozygous dominant for height. So homozygous meaning the same and dominant meaning it's tall. But heterozygous for color, which would be a big Y and a little y. And so this is another opportunity where I want to put this into a cross. And first, before I do that, I have to know what sorts of gametes will each of these parents be able to provide. And so for that, I'm going to use my FOIL method. So the first combination will be a big T and a big Y. The outside will be a big T and a little y. Inside is a little t and a big Y. And then the last is a little t and a little y. So I know exactly what I'm going to put in all of my four columns. The four different combinations. Going to need all four. I'll do the same FOIL method for my second genotype, which is a big T and a big Y. The outside says big T, little y. Inside, that's nothing new, big and big. And then last, big and small. So this is nice. I've got only two possibilities here. And that means all the boxes for these bottom two rows actually will not need at all. So let's go ahead and just do our cross. We're going to keep our T's and our Y's together each time that we do these crosses. Always put the dominant, if it's available, put that first in each genotype. We'll do our second row here. Heterozygous, and heterozygous, homozygous, recessive. Okay, so I did my cross. This is all my potential offspring from this cross for the flowers. And so for this, now what I need to do is basically break down, hey, what's my phenotype ratio? And again, easiest way that I can do that is just, I'm going to go through and underline where I have dominant for both or dominant for just one, and that will show me the relative percentage of phenotypes that I've got. So I'll go through and I'll just put two underlines for any ones that are here where I have dominant for both, the entire first row. And then it looks like 2 out of the 4 in the second row. Okay, so I've got 6 out of 8. So 6 out of 8 are dominant, dominant. And then for the next ones, I've got 1 dominant but recessive. And then for the next box, the last box, I've got dominant and recessive again. So 2 out of the 8 are dominant, recessive. Okay? So again, this is to say that every time I have 6 that are dominant for both, I'm likely to have 2 that are dominant but recessive for color. And so I can reduce that down. I could say that that ratio is 6 to 2, or I could reduce 6 to 2 down to my actual ratio, which is 3 to 1. Okay. And what I'm saying here is basically uh, 3 out of every 4 or 6 out of every 8 are going to be tall and yellow. Okay. So 3 out of 4 tall and yellow. And then I would say that 1 out of every 4 are going to be tall, but they're going to be orange, so not yellow. Okay. All right, so that's my ratio. That's my phenotype ratio. And for this one, it looks like we've got a couple questions that we're now going to answer based off of all this work that we've done. It says, a farmer knows that most people prefer tall and yellow flowers. So if he plans to grow 100 sunflowers from these two parents, how many can be expected to be tall and yellow the way that he wants? Okay, so this is where it goes down. We already did all of the work, right? It says 3 out of every 4 are going to be tall and yellow. We now know that that's desirable. And so if he plans to grow 100 sunflowers, we know 3 out of every 4 are going to be the way that we want them. So 3 out of every 4 is the same thing as saying 75%. And we know 75% of 100, so 75% times 100 is going to equal 75 plants. Okay, so how many plants will be tall and yellow? 75%, which is 75. And then it says, what should be the genotypes of the parent flowers if he wants to make sure that all of the flowers are tall and yellow? And this is a really good question because this is where we can actually use our understanding of genetics and heredity to make decisions about these crosses if we have some control. Okay, keep in mind the only reason why we're getting these orange in the first place is because we have this possibility right here, right, of our little y's, and those come together in these places, right? So they intersect in these places specifically, okay? Now, what should be the genotypes of the parent flowers if he wants to make sure that all of them don't have the potential? If I'm I mean, obviously, one of the surefire ways to take care of this is just to simply make them all completely dominant and homozygous, right? So I could say that all of them together would be dominant homozygous, and there is absolutely no circumstance in which we could possibly have any offspring in this generation or in future generations be anything other than what we want. And if I'm the farmer, truthfully, this is all that I'm actually going to do because I want to make sure that I just sort of nip this short and orange trend in the bud. I really don't want to leave any chance for that. I can make sure that there's no combinations of recessives by just simply taking away the recessives. However, for the sake of this, one surefire way to get away from it is if I looked back here, I could just simply remove that little letter y by just making sure that the possibility for this offspring are, always capital. So it would basically, this is the only two spots in this row where they come together. So I could just get rid of this row by making just parent 2 um, homozygous right here, right? So I could do that where it was just that one parent is different. But again, let's not get overly complicated. If I want to make sure that there are no recessive traits, I'll make sure that there's no recessive alleles. And that's in my best interest if I'm that farmer. All right, let's go ahead and go into problem B. It says, in humans, free earlobes are dominant to attached. Okay, so we're talking about ears, talking about earlobes. So I'll say free earlobes is an uppercase E and attached is a lowercase e. And a straight thumb is dominant to hitchhiker's thumb. If you've ever seen hitchhiker's thumb, it's basically a thumb that can bend back at like nearly a 90-degree angle, whereas straight thumbs are still dominant. Since we're talking about thumbs, I'll say straight are a big T, hitchhikers is a little t. So I'm crossing two people that are heterozygous for both traits. Okay? Now, right away, heterozygous for both traits. I hope that we remember from our guided notes that we have this trend that I can bet my life on. If both parents are heterozygous for both traits, I know for a fact that the phenotype ratio is going to be 9 to 3 to 3 to 1. Okay? And hopefully I remember as well what these relative amounts are. I'll go ahead and break them down just because I do. I know that 9 out of 16 are going to be dominant for both, right? Dominant, dominant. So this would be like free earlobes and straight thumbs. So free and straight would be the majority of them, 9 out of 16. I will have 3 out of 16 that are free earlobes, but then they've got hitchhikers. I'll have 3 out of 16 that are attached earlobes, so attached earlobes, but straight thumb. So I've got dominant for one of the two, just in a different place. And I remember that 1 out of 16 will have the ability to be recessive for both, right? Which is attached earlobes and hitchhiker's thumb. Okay? So, again, I know that the parent genotypes are going to be heterozygous for both, so I can go ahead and just break this down if I want to. Okay, just like that. Um, but here's the thing, guys, when it comes to this, I'm going to still do my FOIL method, where I show that for both parents, basically first results in big E, big T, outside is big E, little t, inside is little e big T. Last is little e little t. It's going to be the same exact thing over here, right? So it's the exact same because the genotypes are the same. And I know that I would then set up those 4 options for my columns and those same 4 options for my rows. And here's the thing, guys. We already know, based on this ratio that's always going to be the case, we know what is what, right? And so why would I take the time to do all of these 16 boxes, knowing I'm going to actually need all 16 boxes, but also knowing that the relative pattern is going to be the same, right? I already know that all of these boxes in this triangle are going to represent my 9 out of 16 free and straight. I already know that these 3 boxes with these dots are going to represent my free and hitchhikers. I know that these 3 boxes are going to represent my attached but straight. And I know that this final box is going to be my recessive for both. So I'm not going to take the time to actually go through and just put all of these letters in there because I already know what the outcome will be. And hopefully you understand that as well. You can always go back to those guided notes, for example, number 1, if you need a refresher on why that is. And so for question number 3 here, it says, what are the chances the parents end up with a child that doesn't look like either of them? Okay, so the child can't look like either of them. I know what they look like, right? So I know that the parents have free earlobes and straight thumbs. And now, really simple, guys. This question is, what are the chances that they end up with a child that doesn't look like them? Right? So this means, what are the chances that the child doesn't get exactly both of these traits? We know that 9 out of 16 are going to look exactly like their parents, or at least the offspring has a 9 out of 16 chance to look like their parents, right? But if I have 9 out of 16 that will, that leaves 7 out of 16 that will not have free earlobes and or straight thumbs, right? I've got 3 of those that would have the free earlobes but not the thumb. 3 of them that would have the attached earlobes. And then one out of the 16 that would have, nothing like the parents, right? So it'd be very confusing. So 7 out of 16 in this case would be the chances that they have offspring or a child that does not look like either of them, since they both look the same. We're going to go ahead and I'm going to flip the page to go to problem C. We got two more that we're going to do. All right. This one says that red roses are dominant to white roses. Okay, so talking about roses here, red is the dominant color, so I can use a big letter R for red and a little letter R for white. And then tall are dominant to short, so again, tall, I can use the big letter T. Short, I'll use the little letter T. It tells me to cross a homozygous red, so homozygous dominant, and short. Okay, so it's homozygous dominant for color, but homozygous recessive for height. So it's going to be red and short. And I cross that with a flower that is white, meaning that it's homozygous recessive for color, but it's heterozygous tall. So that means heterozygous, those two alleles are different, heterozygous. So I'm going to do my FOIL method to see how I might cross these, how the gametes might come together. And this, if I do this, I have first is big R little t, outside is the same, inside, and last. Always the same thing. Very easy for me. That means I do not need any of these three columns. It's always going to be the same. Okay, so I'll do what I've been doing. This is the extent of the time that I'll use. It's just to show that these are exactly the same. And then I'll go ahead and do the same thing for the second parent, right, which is little r big T for first. Outside is little r little t, and then each of those repeat. So I know I don't need either of these two little boxes either, because there's only two types of gametes that the second parent can produce. I'll go ahead and cross to show the potential here. And as I've been doing to show phenotype ratio, I want to underline which ones have dominance and where. It looks like I have one out of the two, so 50%, one out of the two, that could be dominant for both, and only one out of the two that will be dominant for color, but not for height, right? So I know no matter what, I'm going to see red offspring, but I have a 50-50 chance of whether that red offspring are going to be tall or short. So phenotype ratio. It's 1 to 1, right? This means 1 out of 2 are going to be red and tall. That's this one right here. And then 1 out of 2 are going to be red and short. Okay. And so now we're getting into another numerical question. It says if the gardener grows 500 offspring flowers from these parents, how many should he expect to be red and short? Okay, I look up and it says, well, out of 500 or any number that he grows, half of them are going to be that way. So out of 500, half of 500 is 250. So half and half. 250 will be red and short. Now, if he had asked how many will be white and anything, I would say 0, because they can't be white. We'll go ahead and go to our last problem on this practice activity. You'll find that this is another one where I'm not going to take all of the boxes, which is a good thing. In humans, it says thick eyebrows are dominant to narrow. So if thick is dominant, I can just use a big letter T for thick, and narrow, I'll use a little letter t. And they're separated, and separated are dominant to a joined eyebrow or unibrow. Okay, so separated, since we're talking about eyebrows, I can say separated would be dominant, so that's a big letter E, and a unibrow would be a little letter E. So it says, Daniel has a very thick unibrow and is worried that his future children will as well. Okay, that's understandable. So if Daniel has a thick, meaning that he is uh, dominant for eyebrows, worried his future children will as well, then here's the deal. I know that for the unibrow, I know what that portion of his genotype is, and I know at least one of his thickness alleles are big because he does have thick, but I don't really know yet what goes here. It doesn't really specify because I don't know that he's homozygous or heterozygous at this point. I just know it's thick. Now, it does say he's surprised he even has one since his mother has narrow and separated eyebrows, just like his wife. So here's where we get to that heterozygous. If he's confused as to why he even has one, because his mom would have definitely not provided him with one of the two, then we know that his genotype in this case has to be heterozygous, right? And he also knows that since mom didn't give it to him for that thickness, his thickness had to have come from his dad, right? So his mom only gave him the narrow version, right? You can only have narrow if you're both little letter T. So I know that his mom is who gave him a heterozygous genotype as compared with dominant homozygous. Okay, and I also know that basically it says here, so I'm talking about the other partner in this cross, which is his wife Minju, and it says that Minju is just like his mother, right? So she has narrow, meaning that she has narrow two little t's, and separated eyebrows. Okay, so if they're separated, then again, I know that Minju is going to be at least one uppercase letter E. And then it says here, again, it didn't give me enough info. I don't know if it's heterozygous or homozygous, but it says Minju's dad has a unibrow, right? So if he has a unibrow, again, only way that he can have that is if he has two little letter E's. That means Minju's dad had to have given her one of those alleles, and that would be heterozygous. And so again, that's Minju's dad that gave her that. So this is great. Now I'm ready to do my FOIL method. So I can do the first, which is big T, little e. Outside, which is the same. Inside is little t, little e. And last is the same. So I know that for Daniel, the only two things he would provide are those two combination in his sperm. I won't need those right two columns. I'll do FOIL for Minju as well. It looks like she'll be first is little t big E, and then outside is two little t's and e's. Inside we've already got, last we've already got. So good news for me, that means I'm not going to need those bottom two rows because Minju is only capable of creating these two combinations in her eggs. I'll go ahead and cross them as I have been. Hopefully this is a very easy process at this point for you. And finally, there. Okay, I want to know my phenotype ratio, right? So with phenotype ratio, I always do the same thing. Circle, or sorry, not circle, underline where you have dominance. And in this case, it looks like I've got one where it's dominant for both, one where it's dominant for just whether they're separated, and then in this case they would be. Once where it would be dominant just for thickness, and once out of the four, which would be recessive for both. So my phenotype ratio in this case is going to simply be 1 to 1 to 1 to 1. I have an equal chance to see all of these, okay? So Daniel, think back to why we answered this in the first place. Daniel is worried that his future children will look exactly like him, right? That they would have thick unibrows, okay? And in order to get thick unibrows, they would have to be dominant for thickness, but recessive for the fact that they're joined. And so if I'm looking at that, thick would be at least one big T, but unibrow would be recessive. There's only one out of four. Only one out of four that would make his offspring look exactly like him with thick unibrows. So he's got 25% chance of that, about 75 that they won't. But here it asks, what is the chance that Daniel has children who look like him? Well, we just said that. When it comes to chance, it was only one out of the four boxes that apply, right? So that'd only be 25%, right? Or a 1 out of 4 chance. And what is the chance that they will look like his wife, Minju? Again, we have only one trait or combination that Minju has. And since all of them are equal chance, we also know that there is 25% or 1 out of 4 that they could look exactly the same as Minju. Okay, and we'll make sure we remember what we said here. So quarter of the time, or 25% for Daniel, quarter of the time for Minju and Daniel, and 50% chance that they'll get some unique combination that neither of their parents have. And then finally, it says, what is the most likely eyebrow phenotype of their offspring? What is its likelihood? Guys, again, we have 1 to 1 to 1 to 1. 1 out of 4 boxes for all of them, 25% chance for all of them. All we have to say here is that, again, probably a trick question here. All options are equally likely. All options are equally likely. There's not some increased odds. I would say the only thing that would have more likelihood is if we said, you know, is it more likely that they will or will not look like either parent? I mean, still, to look like neither, it's 50% to 50%, but to look like, not one of them, maybe there you'd have some majority, but for this case, yeah, there's no most likely because they're all equally likely, 25% chance for all. And so that is going to actually conclude our practice for dihybrid crosses, and I hope that you found this helpful.